Thank you for coming to this talk. This is joint work with Krishna, where we look at social learning dynamics in different networks. We're looking at a situation where information about an unknown state of the world is dispersed among a society of agents. As these agents take actions based on both their private signals and their observations of their social neighbors, this process of social learning gradually aggregates their decentralized information into some group consensus. Now, how does the social network that determines who sees whom during the learning process, how does that social network affect the efficiency with which these decentralized signals are aggregated? This seems to be an especially relevant question today as technology reshapes our networks. For example, platforms like Facebook and Twitter greatly expand the set of people whose actions we can observe and learn from. The existing theoretical work focuses on learning on the complete network where people observe the actions of all the predecessors, and much less is known about how rational social learning compares across different networks. And the existing results we do have here tend to say that agents will eventually learn completely on all reasonable networks. This then leaves open the question of the impact of a network on how well signals are aggregated. In other words, just how quickly will these rational agents reach that eventually correct consensus? Indeed, in a recent survey, Golub and Sadler say that a significant gap in our knowledge concerns short-run dynamics and rates of learning in these models. In this paper, we introduced a tractable model of rational sequential learning that lets us compare learning dynamics across different networks. And this will give us a fine-grained ranking of networks with respect to their efficiency for social learning. Throughout, we'll be highlighting these network-based informational confounds. To get a sense of what I mean by those, imagine a network where 2 and 3 see 1, but 4 only sees 2 and 3 and not 1. From 4's perspective, 1's action is going to confound the informational content of 2 and 3's behavior. I mean, here, 1's action is almost like an omitted variable. It commonly influences 2 and 3's behavior, but is itself unobserved by 4. And this kind of confounding comes from these intransitivities in observation, which we deem to be realistic in probably all real-world observation networks. We show that this kind of intransitivity can lead to arbitrarily inefficient social learning. Indeed, in generations networks where people move in generations and observe some subset of agents in the previous generation, we express the rate of learning as a simple function of the network parameters, and we also quantify the extent of information loss due to informational confounds. We find that under a symmetry condition on the network, learning is going to aggregate no more than 2 signals worth of information per generation asymptotically, regardless of the size of the generations. Due to the interest of time, I will have to skip the related literature, but I encourage you to pause the video now and to read the slide if you're interested. I will go on to the model. There are 2 equally likely states of the world, 0 or 1. There's a sequence of agents who move in order, each acting once. On her turn, agent I observes a private signal, Si, as well as the actions of her neighbor. So Ni denotes the set of neighbors of I. That's a subset of people who moved before I. I will then pick an action, Ai, in the interval 0, 1, as to minimize the expected square distance between that action and the state. Of course, this utility will cause I to pick the action that corresponds to her posterior belief about the state being 1. The signals are Gaussian and conditionally IID given the state. That is, when the state is 1, they're drawn from the normal distribution with a mean of 1. When the state is 0, from the normal distribution with a mean of -1. The neighborhoods of different agents, which define the network, are going to be common knowledge. A strategy of I is going to specify I's play as a function of I's information. That is, the observed actions from the neighbors, as well as the realization of I's private signal. Now, this is a situation where you only observe earlier agents. And so there is a unique Bayesian Nash equilibrium strategy profile by a kind of forward induction argument, right? There is a unique optimal strategy for the first agent. Now, the second agent who potentially just observes the first agent has a unique best response strategy to that strategy, and so on and so forth. The first result here, and this is what gives the model its tractability, this result says that in any network we can quantify the equilibrium accuracy of every agent in the units of private signals. What do I mean by that? Well, imagine I have an agent I whose only information is n independent signals about the state. Okay? Then for every integer n, I can write down the joint distribution between i's action and the true state. So what I'm writing here is the log action of I, the log of i's action over 1 minus that action, and writing here the conditional distribution of this log action given the state. The plus minus sign here means when the state is 1, well, this log action has a mean of n times 2 over sigma squared. When the state is 0, the mean is instead a negative n times 2 over sigma squared. Right? For different values of n, I have a sequence of more and more accurate distributions of these log actions. What I'm going to do now is to interpolate this countably infinite family of distributions to arrive at a notion of accuracy. I'm going to say social learning aggregates R signals by the I's agent if the equilibrium log action of I has a distribution that looks just like that, except with a possibly non-integer real number R, right, playing this role of n. So here, someone could aggregate 3.5 signals in social learning. So if agents were to use arbitrary strategy profiles, even if they're log linear profiles, then this kind of expression need not hold for any R. But, and this is the content of the next result, equilibrium log actions will always admit this kind of signal counting interpretation. In other words, this R can be viewed as a single sufficient statistic for rational accuracy. So the proposition says, in every network, there are these numbers Ri, so that social learning aggregates Ri signals by agent I. These Ri's do not depend on the precision of the private signals because they're already denominated in the units of private signals, right? So they measure I's equilibrium accuracy in terms of how many units of signals of information are contained in I's action. Now, equilibrium actions of different agents are going to converge to the true state in probability, or in other words, there is complete long-run learning if and only if these Ri's converge to infinity. It turns out that Ri's will converge to infinity for all networks satisfying a very weak condition. This is similar to some related papers that look at learning in networks. But the interpretation of this result, we think, is really that complete long-run learning, whether people get things right in the long run, is not a very good criterion for ranking networks, because all reasonable networks will be tied on that metric, because all of them will satisfy the very weak condition, and thus all lead to correct long-run learning. So what we're going to do here is to compare networks on a different metric. Let's take Ri divided by I. Ri divided by I measures what fraction of the available I signals up to the ith agent are aggregated by social learning. And we're going to take the limit of that expression and call that the aggregative efficiency of the network. This is a measure of what fraction of the signals in the entire society do individuals manage to aggregate under social learning. Of course, just mathematically speaking, we can have Ri's converge to infinity, but this limit of Ri over I be near 0. That corresponds to a case of complete long-run learning, but very slow learning. That's a network where agents eventually converge to the correct consensus, but take a long time to get there. For the rest of the talk, I will be comparing networks for social learning by comparing their aggregative efficiency. So let's start with the simplest network, these things we call the maximal generations networks. So we're going to have some k number of agents per generation, and agents in each generation t are going to observe all agents in the predecessor generation t minus 1. So for example, in the case of k equals to 3, right, 4 observes 1, 2, 3, 5 observes 1, 2, 3, 6 observes 1, 2, 3, and so on and so forth. The result here is that in these maximal generations networks, society will learn completely in the long run with any k. And so generation size doesn't change this eventually correct long-run learning outcome. But aggregative efficiency depends on k, and this is what it is. And what this expression says is that in the long run, social learning is going to aggregate fewer signals per agent when generations are larger, and fewer than 2 signals per generation, regardless of the size of the generation. If you do not like this result that has a "in the long run" clause in it, there is also a short run version of that result. After the second generation, social learning is going to aggregate fewer than 3 signals per generation, regardless of the generation size. So let me try to interpret this result and to try to put it into some context. First of all, notice that in networks that look like this, social learning has to aggregate at least 1 signal per generation. Why? I observe someone's action from the previous generation, which reveals their belief, and I have my own independent signal about the state. So I can use that independent signal to improve this observed predecessor's accuracy by 1 unit, by 1 signal worth of information. Okay, so at least 1 signal has to get aggregated per generation. What the result is saying is that this lower bound of like 1 signal per generation isn't too far from the actual rate of learning, right? What the result tells us is that take our I, divide that by the generation of I. What you get is some number that's less than 2 and some stuff that disappears with I. We're getting no more than 2 signals per generation in the long run, regardless of the generation size. And the short run result says if I were to compare 2 agents who live in successive generations, t and t-1, then this improvement in 1 generation is no larger than 3 signals starting from the 3rd generation. And so, if these generations are large, if k is large, then these bounds of 2 or 3 signals per generation amount to an arbitrarily small fraction of the k available signals that could have been aggregated per generation, and hence we have arbitrarily inefficient social learning. So what's happening here? What's happening here is really informational confounding. Someone who arrives in generation t+1 finds it really hard to figure out generation t's private signals. I mean, she does see all of generation t's actions, but each of these actions is a combination of someone's private signal and their observation of what happened in generation t-1, which is no longer accessible to this person arriving in generation t+1. It turns out this kind of confounding is such a severe statistical problem that we're extracting no more than 2 or 3 signals worth of information out of observing even k actions for k large. Okay, so this result completely characterizes what happens in these maximal generations networks. But now let's move on to more general networks. You might wonder, for example, look at these 2 networks over here, A and B. Which of these 2 networks leads to faster learning? On the left-hand side here, we have our maximal generations network. On the right hand here, network B essentially puts people into 3 slots. Right? So someone who is in the first slot, like person 4 here, observes predecessors in the first and second slots. Someone in the second slot, like 5 over here, observes predecessors in the second and third slots. Someone in the third slot, like 6 over here, observes predecessors in the first and third slots. So which of these 2 leads to faster learning? Well, since we've been talking about how informational confounding is harmful for learning, you might think that network B should do better. After all, actions are less confounded over here. If I look at network A, well, 4 and 5 have exactly the same social observations. Look at network B, 4 and 5 have different neighbors. And so this should make it easier for, let's say, 7 over here to figure out 4 and 5's private signals. But on the other hand, there's also this countervailing force, which suggests that maybe network A should do better, which is simply that, you simply have a larger number of social observations in network A, right? You observe 3 people's actions in network A, but in network B, you only observe 2. And so network B gives you fewer social observations, but also, less informational confounding. Which of these 2 countervailing forces will win? And to answer that question, we really need to compute aggregative efficiency on more general networks, and that is what we'll turn to next. We will look at generations networks with partial observations. Again, keep capital K agents per generation, but now suppose each agent observes a subset of the predecessors in the previous generation. Okay. I'm going to say the network is symmetric if all agents observe D neighbors, so D is like the degree of the network, and all pairs of agents in the same generation shared C common neighbor. So C is like a measure of confounding. So in that network B on the previous slide, that was a symmetric network with D equals to 2 and C equals to 1, right? Each person observed 2 neighbors. And if I take 2 agents in the same generation, the observations overlapped on exactly 1 neighbor. The next result gives you the exact expression for aggregative efficiency in this broader class of symmetric generations networks. If I look at this term in the parentheses, which is telling us how many signals are aggregated per generation, this term in the parentheses increases in D and decreases in C. And these are precisely the 2 countervailing forces I was talking about earlier. More observations speed up the rate of learning per generations, and more confounding slows it down, all else equal. The maximal generations network has the worst possible rate of learning among all symmetric generations networks with the same D. And that is because it has the highest value of C among all such networks. Actions are maximally confounded in the maximal generations networks. So here you might think that in this more general class of networks, perhaps we can do better than get 2 signals worth of information in the long run. The answer is no, you cannot, because again, looking at this expression in the parentheses, as you try different values of D and C, you cannot actually make this expression larger than 2. So the theorem is showing you that this asymptotic bound of 2 signals per generation in fact applies to all such networks, and that's a strengthening of the previous proposition. Now, going back to this question of these 2 networks, which one leads to faster learning? Well, this was a trick question to begin with, because it turns out that if you were to plug in the D and C parameters into the formula on the previous slide, you will get exactly the same answer. In fact, these 2 networks have the same aggregative efficiency. What's happening here is the extra social observations in network A exactly cancel out the reduced informational content of each observation. In summary, we have shown you a tractable model of rational sequential learning that focuses on how the social network affects aggregative efficiency. Generally speaking, the network confounds the informational content of neighbors' behavior and thus leads to information loss. We compute the exact aggregative efficiency in all generations networks with symmetric observations. And we also find that there is significant information loss due to confounding. In any such network, each generation will eventually get no more than 2 signals worth of information, regardless of the size of the generations. Thank you very much.